power LED signal which is 31, which is coming from the IO controller. All right, this is coming from the IO controller. You can see this is coming from the IO controller. So this is okay. This is coming from the IO controller, but that transistor is connected with 5V underscore S3. 5V underscore S3. We'll go to the page number 33. You can see this signal is already out. This signal is already out, but the base is connected with the 5V underscore S3. 5V underscore S3. So from where this 5V underscore S3 is coming? S3, this 5V underscore S3 would come from this 3V 5V regulator IC only when it receives EN1, and EN1 is SLPS4, which is generated after RSM reset, right? So you'll get power, you'll get the RSM reset first, then your power LED will glow, then your power LED will glow, right? This is very important to understand. We'll go back, right? In page number 31 we'll move. So you can see the KBC power button signal would go to the EC of IO controller, then RSM reset would be generated, then you can see in the sequence, then sus clock will come, then S5, S4, S3 will come, after S5, S4, S3, S4 will come, then this power LED will glow because this voltage would come at that point of time. All right, and what is the logic of this signal? This will ground the base, and when this is PNP transistor, in case of PNP transistor, current will move from emitter to collector only when base is grounded, right? We had already discussed in this transistor page. Now we'll go back this RSM reset. Now you can see RSM reset has means it will become active when the voltage is 0, but this is the case of turning off. Right now we are turning on the laptop motherboard. You can see when deasserted, this signal is an indication that the suspend wheels are stable. This signal would only come when all of the 1, 2, 3, 4, 5 will come, and we have already seen this RSM reset is generated via this IO controller. You can see it is generated by the IO controller SB underscore RSM reset. When this IO controller will generate, when the EC inside the IO controller will generate, when it will receive the input, supply, EC reset and clock, and when the power button you press, then this signal would come out, SB underscore RSM reset, and at this point SB underscore RSM reset will be high. We are turning on the laptop motherboard. High means all the suspend wheels are okay. So you have to see 3.3 volt over here. This should come high. This signal will, when this signal will become active, then you are turning off the laptop motherboard, right? This is has, you can see when deasserted, this signal is an indication that the suspend wheels are okay, that is all 1 to 5 are okay. So when you are turning on the motherboard, when you press power button, SB underscore RSM would come, and you can find 3.3 volt over here, 3.3 volt over here. Now after RSM reset, what is our next stage? We'll go to the next stage, and the next stage is LAN underscore RST. In this case, if you search LAN RST has, in this case you can search LAN underscore RST has. This is connected with the PLT reset. So this LAN underscore reset is not active at this point of time. This is not active at this point of time, so we'll move to the next stage. This is PWR BTN hash. Now you can see PWR BTN hash. Sorry, this PWR BTN is connected with the SB underscore power button. Now you can see this is coming from the IO controller. You can see this is coming from the IO controller. Wait. Yes, this is coming from the IO controller. When this signal is coming out, when you press power button KBC underscore PWR BTN, when you press this power button, EC will release RSM reset and SB underscore power button hash. These two signals are directly connected to the ICH. So if these two are not coming, we have to check the IO controller supply reset clock and EC BIOS interaction and KBC power button. If all of them are okay, then, and if ICH is sorted, then also this voltage won't come. So if these voltages are not come, we have to look for IO controller supply reset and clock and EC interaction and the IO controller itself and ICH, right? So these two signals are going to the ICH. Now what is this power button? The power button will cause SMI or SCI to indicate a system request to go to sleep state. If system is already in sleep state, this signal will cause a wake event. Right now we are turning on the laptop motherboard because we are seeing the power sequence from G3 to S0, mechanical off to S0 timing. So when this power button will come, then this will wake up the ICH. Now the ICH will generate the output sus clock, SLPS5, SLPS4 and SLPS3 to open the all voltages. You got my point? You got my point? At this point of time, we have checked the interaction of EC BIOS with IO controller, KBC power button, right? KBC power button, then it will generate the SB underscore power button. It will go to the ICH and the ICH will generate the following output: sus clock, SLPS5, SLPS4, SLPS3. Alright, now we'll check the seventh step, sus clock. Sus clock. What is sus clock? We'll go and check what is sus clock. Sus clock means suspend clock, and you can see this clock is an output of RTC generator circuit to be used by other chips for refresh clock. This is very important, and we can just copy it, test it in a schematic diagram. You can see sus clock, and you see sus clock is an output. And where this is going? This is going to an IC to generate following two clocks. Right now your clock generator is not active. Clock generator is not powered on. So to generate clock at this point of time, the ICH generates sus clock. That's why we call it suspend clock. That's why we call it suspend clock. This suspend clock is going to this IC, and you can see at this IC is also powered by 3D3V underscore S5. 3D3V underscore S5, this voltage has already been generated. So this IC will generate two clocks. And where are these two clocks going? We can just search it. We can just search it. And this is going to the IC, which is a thermal fan controller. That means your thermal fan controller starts working before, right? It start working before. Now we go back and we see this sus clock. This is at one point where it is going. Where is the next clock going at this point of time? Please remember, At this point of time your clock generator is not working, but these two clocks are important because this clock is for the thermal fan controller. So from where clock will come? Clock is coming from the sus clock. And when sus clock will generate? When RSM reset has already been come out. RSM reset has come from the IO controller. This signal is received at the ICH, then such clock is generated. So if such clock is not generated, we have to check the following signals whether RSM reset is generated or not. If RSM reset is generated and such clock is not generated, then the fault is within ICH. All right. So we'll go again and we see where this TPM is basically a security. TPM, you can see TPM IC, TPM32 CLK. This is for a security purpose, right? This is for a security purpose. This IC, TPM IC is present in the notebook motherboard, right? So this also requires clock, and this is turned on before processor, and at this point clock is required, but clock generator has not turned on, so this IC is using the suspend clock. All right, now sus clock had come, so now SLPS5 will come, and we'll see what are the uses of SLPS5, S4, S3. We have already spoken about ACPI. We have talked about SLPS4 is for suspend to RAM, SLPS4 is suspend to hard disk, and SLPS3 is suspend to RAM. We'll see these things. Okay, so we have covered till sus clock, and we have seen that sus clock is a very important signal. It provides clock when the clock generator has not turned on, so we can call it as a suspend clock. Now we'll see the following signals: the SLPS5, S4 and S3. Basically S5, S4, S3 is for power plane control, and S5 is for the S5 state, S4 is for S4 sleep control, and S3 is for S3 sleep control. So we'll go in schematic diagram and we'll find how they are generated, right? And also in our power sequence we can see first SLPS5 is coming, then SLPS4 is coming, then SLPS3 is coming. So we'll go in the schematic diagram and we'll find it over here. We'll just zoom it out, and you can see in this SLPS5 is not connected. This is not used, and obviously this is not used because the S5 enable, we have already checked that S5 enable is generated by IO controller. So in this case, in this motherboard, SLPS5 from ICH is not used. It is S5 stage is controlled by IO controller, and I have made a small block diagram showing these things, right? So this is my S5 stage, and we have already discussed the S5 stage earlier, that the IO controller will generate S5 enable, S5 underscore enable. When does IO controller will generate S5 enable? When it gets supply, reset, clock, and it reads the EC inside the IO controller, read the BIOS, EC BIOS, and when we press power button, right? When we press power button, then two signal comes, power button and RSM reset. It is going to the ICH, and S5 enable is coming out from the IO controller. This S5 enable will go to the 3 volt 5 volt regulator, and this 3 volt 5 volt regulator will generate 3.3 suspend volt after switching. So this is all S5 stage, right? S5 means soft off. S5 means soft off. So this is S5 stage. In this case, S5 stage is governed by IO controller via S5 enable signal, whereas if we see if we see the schematic diagram, the ICH, in many kind of board you will find that SLPS5 is active, right? But in this case it is not active. So we'll move to our another next signal, and we'll move to our next signal, and that is SLP_S4. SLP_S4 is for power flame control. This signal shuts off to all non-critical system when in S4 stage. This, you see, SLPS4 has means it will become active when voltage is low. But right now what we are checking? Right now we are checking the G3 mechanical off to S0 timing. We are seeing the power sequence from turn off of notebook to turning on of notebook. But Intel defines everything from the opposite side, that is turning on to turn off. So SLPS4 active, it will become active when it is low voltages. When notebook is getting turned off, then this value would become 0. But right now we are turning on the motherboard, so the volt over here would be 3.3 volt. Now our next signal is SLP_S4. So this will govern the S4 stage. What is S4 stage? Suspend to hard disk, suspend to disk. S3 is suspend to RAM, right? So we'll check SLPS4. Now in the schematic diagram, we can see SLPS4 is going to page number 17, 28, 31, 36, 37, 38. So we'll check each of these pages now, and we can note down the page numbers over here, right? Because if this will open all the voltages in the S4 stage: 17, 28, 31, 36, 37, 38. So we'll go and check all the pages. Now we'll go to the page number. Before going to the page number, let us just check the block diagram that I have made, that will simplify things. And you can see the ICH has got the power button RSM reset from the IO controller. It has generated this sus clock earlier before this stage, and 5 volt reference voltage already there, 1.05 internal voltage is already there, sus 3.3 volt is already there. So this SLPS4 is generated by the IO controller. It will go to the RAM regulator. This is very important. It will go to the RAM regulator. This RAM regulator will switch and generate 1.8 volt, and 1.8 volt is going to the GMCH and memory slot, and these values will change according to the type of notebook motherboard we are using. That is, if this is DDR2, so that's why it is 1.8 volt. If we are using DDR1, this is 2.5 volt. If we are using DDR3, then this is 1.5 volt. And this SLPS4 is also going to the IO controller. Now this is a very simple block diagram. The main thing is generation of RAM volt. The generation of this 1.8 volt, this is VDDQ. We have already discussed over here. Let's go back and see what is this and why it is important. Yes, this is VDDQ. You can see 2.5 volt for DDR1, 1.8 for DDR2, 1.5 volt for DDR3. So this is VDDQ. VDDQ means a stub series termination voltages. This is also called dim voltages. And then we have termination volt and reference volt. So VDDQ is already generated. VDDQ is generated in S4 stage. That's why in S3 stage RAM is already powered on, right? RAM is already powered on because the RAM supply has already come in S4 stage, right? Yes, S4 means suspend to disk. S3 means suspend to RAM. So during S3 RAM supply should have already been turned on. So we can see in the S4 stage RAM supply has already been turned on. So we'll go and check in a schematic. This signal SLPS4 is going to page number 17. So we'll check in page number 17. We'll check in page number 17. Where is this signal? We'll just go back and SLPS4, right? S4, page number 17. So you can see in page number 17, this PM underscore SLPS4 is going to the gate of a MOSFET. This is an N channel MOSFET, right? And what it will do, if it goes to the gate of MOSFET, then the ground would, then the gate of MOSFET, this MOSFET will get turned on. So there will be a path over here. So this 3.3 volt, the ground would shift over here. So this is, you can see, emitter to base. Emitter to base means PNP, right? This is PNP, and in PNP it will become only active when you can tell me PNP. There should be no confusion. So we just see over here, PNP, the base should be less voltage, ground voltage, then it will become active, right? So you see over here, PNP, emitter to base, PNP, the base should become grounded, then current would flow from emitter to collector, that is, it would become active. So we'll see over here, PM underscore SLPS4 is going to the gate. This is a N channel MOSFET. So this MOSFET will turn on. The ground would shift over here. This voltage would become 0 over here. And we can see the base is already at 0 voltages. So this PNP, emitter to collector, current will flow from emitter to collector. This 3.3 volt would go over here because this transistor will get turned on, and this power on, this PWR underscore on volt would get turned on, right? PWR underscore on, and we can see this is PWR underscore on is going to the docking connector and is going to the docking connector. Right now this 5 volt underscore S0 has not been generated because we are in S4 stage. So in S4 stage the docking control should come on, right? In docking control should come on, and you can see the PM underscore SLPS4 will turn this MOSFET. So the ground would shift over here. So the base is now at 0, base is now grounded, and this is PNP. So in PNP, base is grounded, then current will flow from emitter to collector. So this transistor will turn on, and this 3.3 volt would reach over, 3.3 volt would be connected, and since this power on is now generated, and we can see this power on is going to the which page? Power on, and this power on is going to the docking connector. So we understood this thing. Now we go to the page number 28. This PM underscore SLPS4 is going to the various ICs. So we are checking, but the most important of them is that SLPS4 is responsible for generating the RAM voltages, that is dim voltages, that is VDDQ, and that's why it's very important. But we'll go and check where this signal is going. So where now the next page is 28. So we'll move to the page number 28, and we type S4, and you can see this page, this is going to LAN connector, right? LAN connector. So this is basically the shutdown pin, right? Shutdown pin. So this is for turning off. This is for turning off the this LAN controller, right? This is for turning this SLPS4. Here the SLPS4 has, so right now this is 3.3 volt. So this shutdown, that is reverse of this shutdown, so it will give signal to the IC to start, right? It will give signal to the IC to start, right? It will give signal to the IC for starting, and you can see this is, it will give signal to start over here. So, and now we go to the next page number 31 and 31. So this SLPS4 is going to the IO controller. We will see in the later kind of boards, that is, we have been also looking Lenovo Y570. In that case, if the IO controller get this signal, then the IO controller will generate main on and sus on, but in this board, in D2000 board, there is no such response from IO controller. So we have drawn the diagram, diagram like this. You can see SLPS4 is also going to the IO controller. Alright, SLPS4 is also going to the IO controller. Now we'll see which page. 31 we have already seen. We go to the page number 37. This is the most important. You can see this is the most important. This is 1.8 volt regulator, that is, this is RAM regulator, and you can see there are on one. You can see this is on one, on two. This is a dual regulator, and you can see over here the on one is connected to PM_SLPS4. So this on one, this regulator will get on one, then it will generate DH1, DL1, drive high, drive low, and this DH1 is connected to the top gate MOSFET. This DL1 is connected to the bottom gate MOSFET. So this regulator will get VCC and VDD and V plus, that is V plus is connected with the DC bat out and VDD is connected to the 5 volt. So this regulator is getting input, it is getting the enable signal out 1, and what is out 1? Out 1 is connected to PM_SLPS4. This is generated by the ICH. Now these MOSFETs will switch to generate 1.8 volt, and this 1.8 volt VPWR is becoming 1.8 V_S3. So this 1.8 volt is RAM volt, and you can see 1.8 volt _S3, that is, this 1.8 volt will become active in S3 state. And how it is becoming active? Via PM_SLPS4, and this is connected to the max on. This regulator is a dual regulator. It will generate two voltages. You see, it is generated 1.05, it is generating 1.8 volt, but this 1.8 volt will come fast because SLPS4 is coming fast, right? And this on one is going over here. This regulator has already received its inputs, 5 volts and DC bat outs. So this MOSFET will be switched by DH1 and DL1 to generate the RAM voltages. So the main essence of my discussion is this: in S4 stage with signal SLPS4, 1.8 volt RAM volt is generated. Right now we'll go back and check the next signal. What is the next signal? Next signal is SLP_S3, right? SLP_S3. So before we go into the schematic, we'll see what happens in the SLP SLPS3. In SLPS3 you can see it is turning all kind of voltages in the notebook motherboard. So we'll go in the schematic diagram and we'll see SLP underscore S3 hash, right? And you can see this SLP underscore S3 is generated by the ICH, and it is going to how many pages? 28, 22, 28, 31, 34, 37, 38 and 40. So let's write over here. Let's write over here 22, 28, 31, 34, 37, 38 and 40. So we just copy it. The signal, this is very important. S3 means suspend to RAM, S4 means suspend to disk. So during S3 stage, RAM voltages should already be turned on. So that's why this S4 helps to generate the RAM voltage, right? S4 helps to generate RAM volt. Now we'll go and check what this let me copy this, what this SLPS3 does, and we'll go to the page number 22, and we have already come to the page number 22. Now you can see this is PM underscore SLPS3 is going to this IC, and this G792 underscore RST, basically this is thermal IC. So both of them, if both of them are okay, then PM underscore PWR okay is coming on, right? PM underscore PWR okay is coming out of this IC. So this is also very important. Now we go to the next page, that is 28. And you can see in page number 27, okay. So this 27 is going to the LAN IC. So we'll check this part, when we are checking how LAN is working, right? How LAN is working. So we'll go to the next page, that is 28. Yes. And this 28, this is G577, and this is again new card controller. Earlier S4 have come, now S3 is come. The first SLPS4 signal is going to this IC and it gives start signal, right? Now this SLPS3 will remove this new card from the standby section. First it remove the start. This SLPS4 signal started this new card controller, and this SLPS3 started it from the standby condition, right? Started from standby condition. Now we'll go to the 31, and you can see this SLP underscore S3 is going to the IO controller. So we can check this SLP underscore S3 signal at the pin of IO controller, whether S3 has come or not. Now we'll go and check in page number 34. And you can see this is page number 34. This SLPS3, now here it is very important. You can see in this page SLPS3 helps to generate 5 volt underscore S0, 3 volt underscore S0, 1.8 volt underscore S0 from the corresponding voltages, right? And this S3, this PM underscore SLPS3 helps. Now let us check. This is a transistor, right? Arrow is from base to emitter. So this is NPN, right? This is NPN, and we have already studied in NPN this transistor will become active when a high volt, when there will be voltage at base. So this PM underscore SLPS3 has, there will be 3.3 volt during the turning on of the notebook motherboard. We are already discussing that we are turning on the notebook motherboard. When you are turning off, then this voltage would become 0, this transistor won't work. So all these voltages would get 0. You know, the notebook motherboard starts in a sequence. Similarly, the notebook motherboard shuts off in a sequence. Sequence is same. The starting of sequence is same. The turning of sequence is same with a little changes. So right now we are discussing the turning on of the notebook motherboard. So PM underscore SLPS3 has here 3.3 volt would come. Base will become, you see, high voltage at base. So this transistor will turn on, and here before this transistor is turned on, there is no path, right? There is no path. Now ground would get shifted over here, and you can see this is a P channel MOSFET. You can see this is a P channel MOSFET. Arrow is outside. In P channel MOSFET, current will flow from source to drain. When current will flow from source to drain? When VGS is negative. So if ground gets shifted over here, the value at this point would be less than DC bat out, because there is a resistor, so there would be voltage drop. So now voltage at gate is less than voltage at source, so this MOSFET will turn on, and this DC bat out would go to gate. Right, this DC bat out would go to gate. Now this is N channel MOSFET, and in N channel MOSFET we have already discussed that VGS should be greater than certain value. Now at gate you have DC bat out. Obviously DC bat out is higher than 5 volt. So this MOSFET will turn on, and this 5 volt underscore S3 would get passed to 5 volt underscore S0. You understood my point? See, in any schematic diagram, the knowledge of basic electronics is very important. So I reiterate the function of transistor and MOSFET. Right? Reiterate the function of transistor and MOSFET. And if you get these basic things, analyzing a circuit diagram is just a child's play. Here you can see PM underscore SLPS3 generated by ICH. Here 3.3 volt is there. This arrow is outside. Arrow is outside means NPN. Now in NPN we have already discussed base is at higher voltage, then the current would flow from collector to emitter. Current would flow means this transistor will turn on, and this ground will become like a wire, and this point would be get connected to the ground. So if ground is shifted over here, then there is a path, and voltage at this point would be less than DC bat out, because there is a resistor, right? So voltage at gate is less than voltage at source. This is a P channel MOSFET. So P channel MOSFET would get turned on when VGS is less than a specified value. So this current would flow from source to drain, and source to drain. So this MOSFET would turn on. DC bat out would get connected to the gate. Now voltage at gate is higher than voltage at source, so this MOSFET would turn on, and this 5 volt would come over here, right? Similarly is the case for this. You see, all gate are connected like this. Similar is the case. So in this, so SLPS3 signal is responsible for generation of these 3 voltages, right? Generation of these 3 voltages. Now we go to the page number 38. Page number 38. Now you can see this page number 38 is 1.8 volt, 1.05 volt, right? Now you can see this PM underscore SLPS3 is connected to the same RAM regulator IC. You can see this regulator, this RAM regulator is in fact dual regulator. One, it is generating the 1.8 volt. This is already been generated. This has been generated via this signal. Now SLPS3 is connected to the on2. So if it is connected to on2, that means the second regulator will turn on. Drive high to drive high, drive low will turn on this MOSFET. This switch these MOSFETs to generate 1.05 volt. This 1.05 volt underscore PWR is converted into 1.05 volt underscore S0. Right? 1.05 volt is converted into 1.05 volt underscore S0. So this is very important, right? This is very important. Now we go to the next page, that is page number 38. And you can see this page number 38, it is going, you can see this is going to the regulator which generates 1.25 volt. 1.25 volt. You see, PM underscore SLPS4S3 is connected to, sorry, we go back next. In this page, 0.9 volt LDO, 1.25 and 1.5 volt. So this SLPS3 is connected to the enable pin. Vin is 1.8 volt underscore S3. This is already generated. This is RAM volt, right? Vin is already here. Enable is already here. So this V out, this 1.25 LDO, there is no switching. 1.25 volt would come LDO and 1.25 underscore LDO via gap resistor is coming 1.25 underscore S0, and a power OK signal is going on. And what is power OK? CPU core underscore on. Now this CPU core underscore on will generate this CPU core voltages, right? CPU core voltages. But before 1.25 volt has already been generated, before CPU core volt generated, you can see termination voltage is also generated. You can see SLPS4, SLPS3 signal have come over here. SLPS4, SLPS3 signal have already come over here, and VTT REF is connected to DDR underscore VREF underscore S3, and we can check what is this DDR underscore VREF underscore S3. This would be 1.8 volt, and VTT, that is termination voltage, is already generated. So to turn on the RAM, three kind of voltage is required. We have already discussed VDDQ. VDDQ is RAM volt. RAM volt 1.8 volt has already been generated via SLPS4. Termination voltage is now being generated via SLPS4 and SLPS3. So RAM is turned on before CPU. All the three voltages to turn the RAM has already been on. So RAM is now powered on. RAM is now powered on. We can see this DDR VREF under, again this VTT is the LDO output of this IC. So if your 0.9 volt won't come, you have to check this IC. We have to check S5, S3, we have to check the VIN, we have to check the VDDQ QSNS, right? VDDQ QSNS. So before getting the CPU supply, you can see CPU core underscore on. This will generate the CPU core voltages. Before getting the CPU voltages, all the RAM supply turned on. That is VDDQ, termination voltages, and the reference voltages. And you can see this is VTT reference, and this VTT reference is connected. This VTT reference is connected to the this volt, and you can see where this volt is going on, right? DDR VREF underscore S3, and you see this DDR VREF underscore S3 is basically this VTT reference. So there is two output of this regulator, VTT reference and VTT, and how they are generated? They are generated via an IC where VIN is 5 volt underscore S3, it is already generated. S4 and S5 have already come, VDDQ is already come, VDDQ is RAM voltages, so this IC would generate VTT reference and termination voltages. We will see in another schematic diagram that there is a separate IC to do this. In DV2000 board, we have seen that RAM voltage is already generated, but we have talked that there are three kind of RAM voltages: VDDQ, termination volt and reference volt. 1.8 volt is already generated. Now we require 2 more volt, that is reference volt and termination volt. This IC is generating both of them, DDR VREF underscore S3 and VTT. Both are the output of this regulator, right? Now we go to the page number 40. We go to the page number 40. And here also this is coming, and this is 4. You can see page number 40. This is basically the core volt, right? VGA core 1 volt, right? VGA core 1 volt. We'll talk how many kind of voltages is required by the processor. How many kind of voltages are required by the processor? How many kind of voltages are required by the processor? We'll talk about this. This is for VGA core 1 volt, right? This is for the VGA core, and this 1 volt would go to the, now we see the page number 40. Here you can see this page number 40 is generating the VGA core voltages, because we are seeing the schematic of a DV2000 with graphic board. So the graphic processor also need voltages, and you can see this SLP S3 signal is going to the graphic core regulator voltages. It will go to the enable, and this IC will generate drive high and drive low signals, and this switch these MOSFETs to generate the VG underscore core underscore PWR. So if your graphic is not working, you have to first check whether the graphic supply is coming or not. And in the graphic supply, this is VGA core volt, and there are 2 more voltages required for this. This is 1.2 volt regulator, and this 1.2 volt regulator is also getting enabled by SLPS3 signals, and it will output a value of 1.2 volt. And similarly, this is 1.2 volt, and you can see where this 1.2 volt is going. This 1.2 volt, you can search over here, and this 1.2 volt is going to the graphic IC. You can see this space 1.2 volt. You can see this space. This is NB8M, that is, this is the graphic chip, right? This is the graphic chip, and you can see all these regulators are generating a very important signal. CPU core underscore on. Now we will check this signal CPU core underscore on. So we go back to our presentation, and in our presentation we have seen this SLP S5, S4, S3. We have checked what is the effect of this signal, and we go to the timing diagram. In the timing diagram SLP S3, now VCC comes, and you can see what does VCC include. VCC underscore 1.5A, 1.5 VCA, VCC 1.5B, VCC 3 underscore 3, VCC 1.05 volt. These voltages we have already discussed that these have come, but we'll follow the procedure. And you can see, you go back and you see this is the exact sequence of this voltage coming out, V5 REF. Now we go to our presentation and we see what is V5 REF. This is reference for 5 volt tolerance, and this is connected to 5 volt underscore S0. We go into the schematic diagram, we search for V5 REF, and this V5 REF is connected to 5 volt underscore S0, 5 volt underscore S0. So we go and see where this 5 volt underscore S0 is. Five volt underscore S0. So we have to see where this 5 volt underscore S0 have come. Go and check. Yes, we have already discussed the effect of SLP S3 to generate 5V underscore S0. And why this 5V underscore S0 is important? Because this 5 volt underscore S0 is generating the 5 volt REF. So this is important. So if we follow the timing sequence, we'll eventually test all important things. So for testing V5 REF, we had to test this MOSFET, right? We have to test this MOSFET. If you follow this timing sequence, we will test all important things. We can test all important things, right? We can test all important things. So now we go to the next step, and this is VCC 3 underscore 3. What is VCC 3 underscore 3? This is 3.3 volt for core well. We've already checked in the ICH that VCC sus 3.3 generated. That 3.3 is for the suspend well. Now this ICH this 3.3 volt is for the core well, and we can just search this. I have already spoken that there are 3 kind of voltages: RTC well, suspend well, core well. First RTC well will get turned on, second suspend well will turn on, third core well will turn on. Suspend well itself has 3 kind of voltages. One is reference volt, one is 3.3 suspend well input output, another is 1.05 volt internal, right? For logic, 1.05 volt internal, that is for logic. Similarly, there will be 3 volt in the core well, right? And we are going to check VCC 3 underscore 3. So we search VCC underscore 3 underscore 3. Now this VCC 3 underscore 3, you see this is core well. All these voltages are core well, right? So this is connected to 3D3V underscore S0. And how this 3D3V underscore S0 is generated? We go and search over here. This is very important to understand everything, and by following the data sheet timing sequence, we can test any kind of notebook motherboard, and eventually we can locate the actual fault, right? We can locate the actual fault. Now 3D3VS0 is being generated. Let's check from where this is generated, and obviously it will be generated from SLPS4 or S3, right? 3D3VS0, you see, this is SLPS3. We had already discussed this thing. So I am trying to show you that if you follow the timing sequence, we will eventually come to test these things. So the best method to debug any notebook board is to follow the Intel timing sequence, right? To follow the Intel timing sequence. Now this is already covered. VCC is all this thing, you see. Here they have clubbed all these voltages into VCC1. Now VCC1 is this thing. VCC1 is all these voltages. VCC3_3 come. Now VCC1_05 will search this volt. You see, VCC1_05 in this schematic diagram. VCC1_05 is connected to, this is connected to 1.05 volt _0. How this is generated? We go and find out, and this is generated via this regulator, right? This regulator, and we had already discussed on 1, on 2, right? This 1.05 volt is generated from second regulator on 2. That means on 2, that means SLPS3. We had already discussed. Now we go again and we have to find other power. Now what are other powers? Other powers, you see, other power include VCC USB PLL, VCC DMI PLL, VCC SATA PLL, and you can search and find out this. So by following the Intel procedure, you will go and find everything. This is 1.5 volt _S0. Now we go and search how this 1.5 volt _S0 is generated. We go and find it out. You see, this is 1.5 volt _S0. It generated 1.5 LDO is getting converted, and this is getting converted from this signal. You see, 1.5 volt voltage regulator via SLPS3 we had already discussed. So I am going to correlate the way, right? This is the exact way to trace. This is the exact way to trace. Now we again check VCC1_5A. If you trace like this, you won't miss anything, right? And this is the exact correct way, because any small component faulty on notebook motherboard can cause problem, right? But there are so many components. So what is the correct steps? This is like a mathematics formula to solve a problem, right? You can treat this as a mathematical formula to solve any kind of problems if you follow the Intel procedures. Again we check VCC1_5A. We search over here. This is connected to 1.5 volt _S0. It has already been generated, right? Now we check VCC CPU_IO, and the explanation of these signals are already there. Explanation like V_CPU_IO is powered by same supply as processor IO voltages, and this supply is to drive the processor interface signal, and 1_5AB is 1.5 supply for logic and IO. So we'll check this signal. We again test it over here. CPU IO. Now where is going? 1.05 volt is 0. We have already checked. Let us check it again. Let us, you see, we reached at the same point. So like this we can test each of the important regulator, each of the important components, and we will be in a position to solve any problem. Now this is SLPS for S3. Now let us follow the power sequence. What after this? After this, you see, if all the VCC is there, then PWR OK, and this PWR OK is very important. We just go and see PWR OK, and kindly note that in the Intel timing sequence, these all signals are respective to the ICH or PCH. Whether this signal would be input or some would be output. Like PWR OK, if you find it over here, this PWR OK is an input signal. And what is the input? This input is getting by two kind of input. One is PM underscore PWR OK. And what is PM underscore PWR OK? You just search over here and you can see this is generated via this AND IC, and this AND IC is having input PM underscore SLPS3. So this S3 has already been generated, and this G792RST, this is by thermal diode. So this signal would get converted into PM underscore PWR OK. In some kind of notebook motherboard, this PM underscore PWR OK generated by the IO controller after receiving SLPS4 and S3. You see, all SLPS4 and S3 signal is also going to the IO controller. So in some kind of notebook motherboard, you can see this PM underscore power OK is going to two places. One is page number 7, another is page number 20. And which is page number 20? This is, you see, PM underscore PWR OK, and it is also going to the page number 7. You see, right? This PM underscore PWR OK okay, so now we have seen all the voltages that have been generated, that is VCC, and the VCC, we have seen VCC compromises many kind of voltages. Now we come to the step number 12, that is power OK. You can see the power sequence, and in the power sequence, after VCC generated, power OK is a required input for the ICH. So we'll go to the circuit diagram, we search PWR OK and we have to go to the ICH page, right? This is not ICH page, this is North Bridge. So yeah, so this is, you can see power OK is a required input for the ICH, and this input is required after VCC. So everything is in sequence, so we have to just follow this sequence. Now PWR OK, let's see from where it's getting generated. This PWR, we just let it just copy it up, and before we see from where PWR OK, let's see what is the definition of PWR OK. When asserted, PWR OK is an indication to ICH9 that all power rails have been stable for 99 milliseconds and that PCI CLK has been stable for 1 millisecond. So this is very important. Power OK indicates to the ICH that all the power rails of ICH is OK, right? Okay, so let's see from where this PWR OK is getting input, and this is getting input from a signal PM PWR OK. So we'll select it and we'll check from where this signal is coming, right? And this is coming from this IC, this AND IC, and this inputs is SLPS3 and the reset from the thermal IC. So in many kind of notebook motherboard, you'll find this PWROK generation is little bit different than this data sheet. And for our discussion, we are already referencing three kind of circuit diagram. One is DB2000, another is Lenovo Y570, and another is R12. So I will be covering all these three circuit diagrams in detail, and I would tell you the differences between them. What is more important is the signal name. The signal, we have to just trace it out from where it's coming. Now we go to the next stage. And the next stage is VRM power good. You can see in the data sheet as well. After power OK, VRM power good. VRM power good. So we see over here what is VRM power good. What is the meaning of this VRM power good? VRM power good is an input to ICH, and this signal should be connected to the processor VRM power good, signifying that the VRM is stable. So this VRM power good is an input to the ICH, indicating that the CPU core voltage regulator is working okay, right? And you can see this signal is internally ANDed with the power OK input. That is, inside the ICH, this power OK and VRM power good is internally connected. Now we go into the data sheet and see from where this VRM power good is okay. According to the definition, VRM power good is coming from the CPU core voltage regulator. We can also see in the schematic diagram. Now you can see VRM power good is fed by this signal V gate power good. Now let's copy this, and V gate power good is coming from the core voltage regulator. Yes, this is the core voltage regulator. You can see CPU core voltage is being generated, and before analyzing this regulator, let's understand something about the CPU core supply. In many kind of notebook motherboard, you will find different types of core voltage regulator. So how those core voltage regulators are implemented? You can see here there are VID pins. In some kind of regulator you won't find this VID pins. So let us understand about the specifications of CPU core voltage regulator. After understanding the specification, we'll come back at this point and understand this core voltage regulator. Let's go in our presentation, and in my presentation I have prepared about the CPU power delivery. Now this point I have talked is about the recent kind of notebook motherboard, that is how many types of voltages are required by processor. You can see VCC is the voltage supply for the core rail of processor. VXG is the graphic core rail of processor. Here I am talking about the latest kind of processor, the processor which is integrated memory controller, which is integrated graphic controller, right? I'm talking about that. So VCC is the supply for the core rail of processor. VXG is the graphics core rail of processor. VTT is the uncore rail of processor. Since now the part of GMCH is in the CPU and the remaining part of GMCH in the south bridge, the memory controller is in the CPU, so VTT voltage is required. Earlier in this case, in DB2000 board, if you search for VTT, you will find it in north bridge. You can see, you can find it in north bridge. VTT. Wait. Yes, here this is the north bridge, but right now I am talking about the latest kind of processor. In latest kind of processor, the memory controller has moved to the CPU. There is an integrated graphic processor, integrated graphics in the CPU. So that kind of CPU require this kind of voltages. One is VCC, another is VXG, the third is VTT, and fourth is VCC PLL. VCC PLL is required for the PLL clock generators present on the CPU, and then VDDQ because the memory controller is on the processor, so VDDQ and VTT is on the CPU, right? Let's go to the next slide, and in the next slide you can see how the processor requires this kind of voltage. You can see VCC is for the core rail, right, and VCC PLL is for the PLL part, VTT, and you see VXG and VDDQ. All the CPU requires this all kind of voltages. This is for the latest kind of processor. Latest kind, that is Arendelle processor is a latest kind which supports Intel Series 5 chipset. Intel Series 5 chipset. We have already talked about this. Now let us come to the main point. The Intel core power specifications. This is very important. Earlier, when there were no, we talk about IMVP. What is IMVP? IMVP stands for Intel Mobile Positioning, Intel Mobile Voltage Positioning. And what does this mean? If any regulator adhere to the IMVP specification, if any regulator adhere to the IMVP specification, then that regulator will lower down the VCC under the full load condition. And what does this mean? Suppose your processor is running graphic intensive programs. In that graphic intensive program, lot of current is required, that is load is high. So at high load the VCC will get reduced. And what is the advantage in reducing the VCC? When VCC is reduced, the power consumption is less, that is heat generated is less. And if the regulator does not implement the IMVP, VCC will remain same, and that will cause a greater power loss, greater heat generation during the high load condition. What do you mean by high load? Load always refers to the current. Please mind it. Load always refers to current. So if high load, that means heavy current is required, and during heavy current condition, the IMVP regulator reduces the VCC. You can see VCC is 1.60 volt. This is light load when there is a requirement of less current, but when there is a requirement of high current, you can see the VCC is reduced. Similarly, all kinds of voltage regulator now present in the notebook motherboard adheres to the IMVP specification. And what is IMVP? IMVP stands for Intel Mobile Voltage Positioning, and this is Intel Mobile Voltage Positioning. That is, the VCC is dynamic, it's not fixed. That is the CPU core volt. The CPU core volt we can get to see. We get EWRGD. You can see in this page, this core volt is not fixed, it's dynamic between some ranges, and this is what IMVP stands for. That is, in IMVP condition, the VCC, the core VCC will change according to the light load and full load. And how does the processor get to know light load and full load? Via various signals between the regulator and the processor, and we'll understand these various signals. We are trying to make it as simpler as possible so that you can understand any kind of regulators, right? And here I will take two examples of regulators and we'll discuss these things. Let's go to the next page. Intel has come up with various specifications with gradual developments and technology, and first they started with IMVP1, and I could not find any regulators. Actually I cannot find it. Maybe you can find it better. Which are the regulators which adheres to the IMVP1 specification? First, this was the first specification released by Intel for voltage regulators, right? And Intel always releases two kind of specification for voltage regulator. One is VRM, another is EVRD. VRM is a separate card present in some kind of desktop motherboard. In that, VRM regulator is not on the notebook, is not on the desktop motherboard. A separate card is there for them. VRM specifications is there, that is, they are called VRM, whereas EVRD are type of voltage regulator which are present on the desktop motherboard or on the notebook motherboard. Right now we are talking about EVRD. So when I tell VRM, I mean EVRD, because VRM, technically VRM is a different card, is a standalone card which is fixed on the motherboard to supply power to the CPU, right? Intel defines two kinds, VRM and EVRD. Alright, so EVRD, right now when I speak VRM, I'm talking about EVRD because all the notebook regulators are fixed onto the boards, right? These are the specifications Intel have released for Intel mobile voltage positioning, and these specifications are meant for notebook motherboards, right? These specifications, these IMVP specifications are meant for the notebook motherboards. So the first is IMVP1, second is IMVP2, and you can check Max 1718 is a voltage regulator that complies with the IMVP2 specifications, and then IMVP3 is there, and I have given example of LTC 3716. Then we have IMVP4, and this is Semtech SC450. Then we have IMVP5 ADP3206, and we have IMVP6, and we have IMVP7. So what I will do is I will try to discuss these two specifications here, IMVP6 and 7, because these are latest, and when I talk about these specifications, you will always correlate this specification with the earlier version, and also with the coming version. Once we learn how to study these specifications, it's very easy to understand electronics. These are all man-made things, and man-made things can always be broken into smaller parts, right? Understanding natural things require lot many research, right? But these things are already designed by Intel. What we are doing is doing it in a sequential way, right? Doing it in a sequential way. Now we go to the next page, and this is a very basic CPU voltage regulator block diagram, and this is very important. Any voltage regulator will have 6 parts. You can see in the diagram, any voltage regulator, any CPU voltage regulator will have 6 parts. First is power in, that is input. Second is power out, that is type of output that has to be generated by this VRM. Then the third is the various control signals. Fourth is the various output indicators. Fifth is the environmental condition, and the sixth is the mechanical guidelines. We go in the next slide, and you see power in aspects. Power in aspects refer to the type of input voltages that is required by the VRM, and of course power in here you can see in the data sheet, you can see in the schematic diagram, the power in is, you can see power in is VDD VCC, VDD VCC, VDD VCC, VDD VCC. Now we go to the next page, and second is power out specifications, refers to which output energy must be delivered to the load, right? Which output energy must be delivered to the load. So here in the output characteristic we can see the type of that, how much voltages is required by the CPU core voltage regulator. Okay, so now we go to the slideshow. Okay, so we have already discussed that power in aspects means the input of the VR. Okay, the input of this VR, you can see here is the input of the VR. And the second is power out specification, refers to the form in which the output energy must be delivered to the load. And the third is the control signals. What are the various control signals? And you can see what are the control signals: the voltage identification and the load line select. You can see over here in the data sheet what are the control signals: the VID pins, and you can see deep sleep and PSI. We'll discuss about these things, what are these things and how they are important, right? And let's check again the output indicators. Output indicators means the finalization of a startup sequence, VR overheating, and load line regulation. That means we get power good signals. So these are the 5 things that any voltage regulator will have. And here you can see the voltage regulator block diagram. I am referencing here the IMVP 6.5 voltage regulator, and what are the important points you can see. These are the inputs V in, V5, V3. These are the inputs to the regulators, and the output is VCC core to the processor. And you can see to turn on this regulator, VR on is required, and VR on is provided by the platform logic, that a VR on is provided by the notebook motherboard components. And we will see over here from where this VR underscore on is coming, from where this VR underscore on is coming. And you can see this IMVP core voltage regulator also output clock enabled to the clock generator, and this voltage regulator also output VRTT. VRTT is for the proc hot. It indicates to the processor about the thermal monitoring, thermal condition of this regulators, right? Thermal condition of this regulator. And this IMVP regulates its VCC core via this VID pins. VID is given by the processor to the core voltage regulators, right? And PSI and proc deep sleep VR. What this means? Proc deep sleep. This is a signal given by the processor to the regulator that indicates that it is entering a low power state. In low power state, it indicates to the voltage regulator that it is entering a low power state. So we'll understand all these signals, and this is a very good block diagram of core voltage regulator. Now let us find a IMVP 6.5 type of voltage regulator, and I have taken ADP3212. This is very famous voltage regulator, and this is adhering to the IMVP 6.5 specifications. So let's study about the ADP3212, and you can see over here, fully compatible with the Intel IMVP 6.5 specifications, right? It is fully compatible with that. Now, since we have seen the block diagram, that is, input is there, VR on is there, IMVP power good is given to the PCH, then PCH gives VCC power good 0 and 1. What are the exact power on sequence of this voltage regulator? We have to also study about that. What is the exact power on sequence? And you can see this is the exact power on sequence for a voltage regulator. First VCC will come. That is, in the data sheet you can see first VCC will come, and also in our ADP3212 we'll see over here. We'll go to the next page. We'll see the circuit diagram of ADP3212. This is IMVP 6.5 specification, and very good, in fact widely used voltage regulator. This is widely used voltage regulators, and you can see this is a power on sequence. This is power up sequence from ADP3212. First VCC is 0, it will ramp, VCC will ramp, it will go to 5 volts. Similarly over here, VCC will ramp to 5 volt. Now what is the next step? Shut down, SHDN. Now where is SHDN connected to? SHDN is connected to CPU core underscore on, and from where this CPU core underscore on is coming? CPU core underscore on is coming from the power of all important voltage regulator. We can see in page number 36, 37, 38, 40. Let's go to page number 36, and we have to find the CPU core on, right? You can see this is CPU core on, and which regulator is this? This is 3.3 3 volt, 5 volt regulator. So CPU core on is getting generated from the power good of all important voltage regulators. Let's go back to the next page. From 37, let's go to the 37, and you can see this is also a very important voltage regulator. This is RAM voltage regulator 1.8. From here also you can see power good is coming, which is CPU core on 37. Now we go back and we see what is the next page. So we have already seen the power good from 3 volt, 5 volt, 1.8 RAM regulator, and we go to the page number 38. And you can see 38 page number. This is also 1.5 voltage regulator. Here also power OK is going to the CPU core underscore on, which is fed to the shutdown pin of regulator. Shutdown pin of the regulator. Now we go again. Shutdown pin of regulator. So this shutdown will become active when the voltage here is at less. But right now we are turning on this regulator, and here the voltage is 3.3 volt, so it will turn on this regulator. And here we are seeing the power sequence. First VCC is coming, second shutdown is coming, and third VID is invalid. Right now VID is invalid, right? Because VID is invalid. The second is CPU core voltage will ramp to V boot. This is very important. You can see VCC have come, enable is VR on, and V core is ramping to the V boot. What is V boot? V boot is all voltage regulator manufacturer defines a V boot. That is, this voltage regulator will start working and will reach a value of V boot which is defined for that voltage regulator. After V boot has been achieved, then this processor VID will alter that V boot, that is, in some kind of notebook motherboard where V boot is defined, then even if you have removed out the processor, you will find some voltages at here. You will find some voltage at the coil. And what is that volt? That volt is V boot. It's not core volt. Remember, it's not core volt, it is V boot. After you put the processor inside it, the VID values will calibrate this V boot to VCC core, and there is a entire table of this VID. You can see in that data sheet. But what is important to understand here is, if we have removed the processor, even though you can find some voltage value at this point, and what is that value? That is V boot. You can see in the data sheet of ADP3212, V core is reaching to the V boot, and here in our presentation you can see the 1.2 volt is defined for the IMAP 6.5. so the CPU core voltage regulator will go to 1.2 volt. It will soft start, and then VID, you see there is invalid VID does not work while soft start. When CPU voltage regulator is in soft start, initially starting, these VID values will not alter the values. After it gets the V boot, then the VID values will alter this V boot voltages to achieve the CPU core, right? This is very important. First VCC have come, right? Second shutdown pin, that is VR on, and VR on is coming from CPU core on. CPU core on is power good of all important voltage regulators, and third is the VID input. Right now the VID inputs is invalid. CPU core voltage regulator will now start. It will give drive high, drive low to to switch these MOSFETs to generate the VCC core, not VCC core, to generate the VBOOT voltage. After the VBOOT voltage has been generated, the VID pins, the VID inputs from the processor, will alter the VBOOT to VCC core. This sequence is the most important. And after that, clock enable would be out. When VCC core is generated, clock enable is out. You can see clock enable is out. This will enable the clock generator. So after VCC core is generated, your clock generator is started. This is a very important point, and we have to note it again and again. How this voltage regulator is generating power, how this voltage regulator is working. You can see first VCC achieved, second VR on. From where VR on is coming? From CPU power good, from all important voltage regulator. VID will not work initially. CPU core voltage will start, drive high, drive low will switch to produce VBOOT. Then VID values will alter this VBOOT to generate the CPU core voltage. Then clock enable output would be generated by the regulator, and after that PWRGD. You can see PWRGD is IMVP power okay. PWRGT is IMVP power good, and this is feeded to the ICH. So this is the whole step of generating the VGate power good. How VGate power good is generated? First, the core voltage regulator will get input. This is step number 1. VR on, that is CPU core on. This is coming from the power good of important voltage regulator. It will come. Now the voltage regulator will start in the soft start. Drive high, drive low will come. It will switch this MOSFET to generate VBOOT. After VBOOT is generated, CPU VID values will alter the VBOOT to generate VCC core. VCC core will get generated, and clock enable is out. After clock enable is out, then IMVP power okay is out. So this is the exact power sequence. Of turning on of voltage regulators, right? Now we'll see all the things that we have discussed is written over here, so that you can just go through these things. And something that we have not discussed is proc DPR SLVR. Proc DPR SLVR is an input signal to the IMP 6.5 compliant controller. It indicates a low power mode, and processor uses this line during power up. So this is basically initially the processor will use DPR SLPVR because initially the processor is at light low condition, so it will indicate to the regulator that yes, it is under light load, right? And the second thing is power status indicator. This is an input signal to the IMVP 6.4 compliant controller. It indicates maximum possible load current at given processor frequency, right? This will indicate power status indicator. You can see over here the PSI, from where this PSI is coming. PSI is coming from page number 5, and here you can see the page number 5, right? And this is processor. This power status indicator is coming from the processor to the regulator. It indicates the current indication, right? Current state of power. So this is also very important. And but most of the thing is turning on of the voltage regulator. We have studied the turning on, how processor is turned on. Now next point is iSense. iSense is a required controller output signal. The controller must output must monitor output load current and report it to the processor. I sense is basically this voltage regulator will sense the output current, and will feed it to the processor, right? And we can see over here also there will be some signal going from voltage regulator to the processor, indicating the output current. Like you can see VCC and VSS sense is also coming from the page number 5. You can see VSS sense is coming from the, you can see this VCC sense and VSS sense. This is coming from the processor to the regulator. It indicates the CPU voltage, because there must be some feedback loop, right? There must be some feedback loop. We go back, like in the block diagram you can see I-sense is going from the regulator to the processor. The processor will get to know the output value of the current, right? And the processor will give feedback to the regulator about the VCC sense and VSS sense. So if there is any drop in the values of this, then the regulator will adjust the VCC code. So this is a feedback loop, right? This is a feedback loop. PSI indicates the current power status. DPSLVR indicates the light load condition. I-sense will give an indication to the processor about the current output current value, and the VCC and VSS sense will indicate the current voltage at the processor. So this is all about the feedback circuit. The most important thing that we have discussed here is VCC, shutdown, VID, VBoot, the soft start, then clock enable, then power good, and remaining are sideband signals. What are the sideband signals? VCC, VSS sense for giving indication to the voltage regulator about the current voltage value, and I-sense is indication of the output current, and again there is a VR_TT. You can also see over here, we go back. Yes, that is VR hot. You can see VR hot is VRTT, and this is going to the CPU proc hot. This is again going to the processor. If the regulator thinks that a thermal overheating condition is coming on, then it will indicate CPU processor heat, CPU proc hot. And how does this voltage regulator get to know that it is overheating? Via the VSS sense, VCC sense, and I-sense, right? And I-sense, these are the feedback loop, right? These are the feedback loop. What is most important to understand here is the turning on of this voltage regulator, and we had discussed how does it get turned on. You can see an example like ADP 3212, first VCC come, then VR on is come, then VBoot is building. Before VBoot, VID will not be treated. After VBoot, VID will treated, and it will calibrate the VBoot to VCC code. Then clock enable out is coming on, and power good is coming on, and this power good is IMVP power good is VGate power good. So now we have come to this sequence. My VRM power good have come to the ICH. Now we go to see the next signal, that is sus_stat. So if we follow this power sequence, we can solve the minutest of problems on the notebook motherboard. We should be very much clear of the exact sequence. What I'm trying to describe here is the exact sequence, because people often get confused when VRM power good will come out, when power OK will come, when VCC will come. This is the exact power sequence. So before you see my videos, I would request you to delete all the previous concepts that you have. These concepts are all correct and in line with the Intel schematic, Intel data sheet, right? Okay, so now we have checked the VRM power good, and how this VRM power good is coming. This is coming after generation of the CPU core supply, right? CPU core supply. So we go to the next step, clock generator. Now you can see the CPU. We go back into the VGate power good. We go back. Yeah, so we go back to the core voltage regulator. You can see here this core voltage regulator, after generating the core voltage supply, it will generate the clock enable signal and the IMVP power. Okay, this is going to the ICH, and clock enable, you can see over here CLKEN has, this is going to a MOSFET, and that MOSFET is generating the CK power good and VRM power good. The CK power good, we just check over here where the CK power good is going. The CK power good is going to this CK power good is going to the ICH, and then this CK power good is also generated back from the ICH, and it is going to the, you can see, to the clock generator. You can see this is going to the clock generator. CK power good is going to the clock generator. So this clock generator has already got its input 3.3 volt, 1.25 volt. Clock enable have come. Now clock enable will come. This clock generator will generate the various kind of clocks required by the notebook motherboard, and you can check whether this clock generator is working or not. You can just measure with CRO. At this point you have to see 48 megahertz. We have already discussed this part, clock generator, previously also. So everything is correlated. You see, clock generator is working after the CPU gets power supply, is working after the CPU gets power supply. Now one thing I've forgotten is, we have discussed the IMVP 6.5. Let us take an example of latest kind of voltage regulator, and this is ISL 95831. So what is the difference between the latest voltage regulator? This is IMVP 7. So what is the basic difference between IMVP 7, and we open the specification of IMVP 7, and you can see the IMVP 7 have included the SVID, the common serial VID interface, and we can understand it much better if we open our schematic diagram, Lenovo Y570, because here the ISL is used, right? The ISL is used, and we go to the page number 49, and you can see this is the ISL 95831 HRTZ, and this is a IMVP 7. Here you are not finding any VID inputs. Do you find? Can you tell me where are the VID pins? Instead of those VID pins, IMVP 7 have implemented 3 inputs: serial clock, serial data, and alert. Why are these 3 pins? CPU communicates the VID data with the voltage regulator. This is the most important difference between a IMVP 7 and IMVP 6.5. In a IMVP 6.5, you go back. Let's go to the VGate PWRGD. I don't remember the page in which the voltage regulator is there. Yes, instead of these 1, 2, 3, 4, 5, 6, 7 lines, IMVP 7 does the same work with only 3 lines, and this is a serial VID interface. The VID values are communicated onto these 3 lines: serial clock, serial data, and alert pins, right? And alert pins. Why are these 3 pins? The CPU communicates the VID values with the processor. This is the basic difference. And moreover, You can go in the ISL 95831 HRTZ and you will see the, let's see the power sequence of this volt. And you see this is the power sequence. Basically this regulator, since this is IMVP7 regulator and this is used in the latest kind of notebook motherboard where the processor is also having the graphic inside it. So this type of regulator is 3+1. 3 means 3 phase for the CPU core supply and 1 phase for the graphic supply. So this IMVP7 is having 2 voltage regulator inside it, whereas you see an example of IMVP 6.5, you find only 1 voltage regulator. This is for the core supply only, whereas you see IMVP 7 voltage regulator, this is 3+1. 3 means 3 phase. This voltage regulator can operate in 3 phase and can supply 3 phase supply to the CPU core supply, and +1 is for the graphic supply. +1 is for the graphic supply. So let us see the power on sequence for the first VR1. We are interested in the power sequence for the core voltage regulator, right? Core voltage regulator. So we will see the power sequence for the core voltage regulator, how it is different. You can see this is the VR1 soft start waveform. First voltage, input voltage have come, second VR on is come, then VID values will correct this V boot to V core, then power good is out and alert signal is given to the processor that yes, it has received the VID, it has corrected the values, it has corrected the value. In the latest kind of core voltage regulator, that is IMVP7 voltage regulator, you cannot find values. You won't find values over here. You won't find values at this point. You won't find values at this point if your processor is not inserted. Can you give me a simple reason why is that? In a 2 chipset where north bridge, south bridge is there, you can measure, you can get some voltage value at the this inductor when processor is not inserted. We call it V boot, right? But here you won't find that values. You won't find these values because when you do not insert processor, this voltage regulator will not turn on. Yes, and why it won't turn on? Because it requires VR on. VR on, from where this VR on is coming? VR on is coming from the power output of all voltage regulator, all important voltage regulator. And since the CPU has embedded memory controller, the voltage VDDQ is already generated. It has to be generated. VDDQ is already generated because the memory controller is inside CPU. So if you do not put processor, your VDDQ is not, VDDQ will not generate, and hence your VR on will not generate, and hence your notebook mother won't work, right? So people often get confused because somewhere in the internet some people show me that when you remove processor you can measure the voltage at the CPU socket. This is true. This is true only for a dual kind of chipset. You cannot find the values in a latest kind of notebook motherboard where processor, because the processor itself has a memory controller. And we move to the more advanced technology where you find the processor embedded in the notebook motherboard. You won't find socket even, right? So we are going towards more advanced technology. So if you do not insert the processor in this kind of notebook motherboard, you won't find the values at these inductors. Whereas in an older kind of boards, you will find some values, and that value is V boot. We have already discussed. All right. That is, so this is a major difference between IMVP7 and IMVP 6.5. What are the major differences? First, the VID lines have been the 7 VID lines have been changed into 3 lines only, that is serial clock, serial data and alert pins, right? This is one major difference. Another major difference, you won't find values over here because the memory controller is already inside the CPU, and hence VR on, it will get VR on only when the memory will get the VDDQ. So you won't find values over here if your processor is not. If you do not put processor into the notebook motherboard, that processor will not turn on. So for checking this kind of notebook motherboard, you have to put the processor inside the socket, right? Whereas in the earlier kind of board, you will find some values that is VBoot. When you put the processor back, the VID values will auto correct to generate the VCC core. Alright, so this is the process is same. First the regulator will reach VBoot, then VID values will auto correct to give VCC core. The process is same, but there are some subtle difference between the technologies that we have already discussed, right? So we go back to the power slide. Now VRM power good is generated, clock generated is also enabled, and it is providing the clock signal to all the various portion of the notebook motherboard. And we have checked how to check a clock generator. I have already discussed this clock generator previously also. The most important thing that is requires is clock enable signals, right? Now we go to the next slide, and yeah, so the next signal is sus underscore stat, and you can see this sus underscore stat. This is sus underscore stat. And what is sus underscore stat? What is the meaning of sus underscore stat? Sus underscore stat means suspend status. Suspend status. And this signal is asserted by ICH to indicate that system will be entering a low power state, right? But right now we are talking about turning on of the laptop motherboard. So the sus stat value would be high during the turning on. You see, the sus stat value would be high during the turning on. You see, it will go to high. It will go to high. Similarly, when you turn off the notebook motherboard, it will go from high to low. So sus stat, we search in the schematic diagram, sus underscore stat has, and you see it is going to the LPC underscore PD. LPC underscore PD has. LPC underscore PD. So you can check this sus stat signal at this TPM IC. Also you can check at this TPM IC. So this is, you can treat this to be a testing point. This is a very good testing point to check sus stat. If sus stat is coming, that means all the power sequence below this sus stat is okay, right? So this is a very good testing point, right? This is very good testing point. What is the work of this sus stat? This sus stat is basically, this can be monitored. This gives suspend status. This can be monitored by devices with memory that need to switch from normal refresh to suspend refresh mode. That is, if your notebook motherboard is entering to in a suspend status. Suspend status means there are two kind of suspend status: suspend to RAM, suspend to disk. Then this signal will notify all devices that the notebook motherboard is entering into this suspended status. It has no specific meaning with regard to the powering on, but it has a meaning with regard to the devices which have to shift itself to a suspend refresh mode, right? Suspend refresh mode. Now after sus stat, PLT reset will come, and this signal is very important. You can see in this block diagram, the ICH, I have already told, the power OK and VRM power good is internally ANDed inside the ICH. So 1 to ICH. Now ICH will generate two signals. One is CPU PWR GD and PLT reset. You can see CPU PWR GD, CPU PWR GD, and you can see CPU PWR GD is generated by the ICH. It is generated by the ICH when it receives power OK and VRM power good. Both of this signal is internally ANDed to generate CPU power good, which is going to the CPU. You see, CPU power good. Let's see again. H power good. Let's copy it. Just copy it. This whole process is so interesting. So many things are correlated, you know. But if you know the exact sequence, that's very important. H power good. You see, H power good is going to the processor, is going to the processor. You can see this is processor page. So how this is generated? First power OK, VRM power good, then it is generating CPU power good, and the fourth is the PLT reset. This PLT reset is going to the reset pin of GMCH, the reset pin of north bridge, and the north bridge will generate CPU reset, and that will turn on, that will reset the processor. After getting CPU reset, processor will read BIOS and will give display. We'll discuss how the processor will read BIOS, but this sequence is very important, very important. After ICH gets power OK and VRM power good, ICH generates CPU power good, ICH generate PLT reset. We can see over here PLT reset. This is very important. PLT RST has PLT reset. You can see ICH is generating PLT reset. It is going to via a and IC PLT reset 1, and it is going to several places. So if you measure this PLT reset, that means your ICH has worked correctly during the power on sequence, because this is the final you see, this is the final thing. This is the PLT reset is the final signal generated by the ICH. After this processor interface signal will come, a stop clock will come, DMI message will come. You see, after the ICH give PLT reset to the north bridge will generate CPU reset. We are discussing a ICH 8-9 board. We'll discuss Intel Series 5 chipset, and this whole signal, this whole sequence will be different in an Intel Series 5 chipset. Right now I am talking about ICH 8 and 9. So what happens? Power OK, VRM power good is received by ICH. It generates CPU power good, which is going to the CPU. That will indicate to the processor that yes, my power is okay. PLT reset is generated by the ICH, and it is going to the GMCH. GMCH will generate CPU RST hash. We can check this signal, CPU RST hash, CPU RST hash, and you see the CPU RST hash is going to the CPU RST hash. You see, CPU RST hash, CPU reset. This CPU reset is going to the, this CPU reset is coming from the MCH to the CPU, MCH to the CPU, and we go to the next slide. Okay, so you see ICH after getting the power OK and VRM power good generates CPU power good. The power OK and VRM power good is internally ANDed. It is given to the CPU in form of CPU power good, and it generates PLT reset. You see in the data sheet, PLT reset is generated, and PLT reset is feeded to the MCH at the reset pin. In the next page you see RSTIN. This signal basically resets the GMCH logic, and after the GMCH gets the reset in, GMCH will output CPU reset signal to the CPU, and after getting the CPU reset, you see after the GMCH asserts its CPU reset hash while reset in is asserted, and for approximately 1 millisecond after reset in is deasserted. That is, after reset in a deasserted, that is after it gets 3.3 volt here, MCH gets 3.3 volt at RST in, then GMCH will generate its CPU reset, and this its CPU reset allows processor to begin execution in a non-state. Non-state means the processor will now start reading from the BIOS. We can see in the schematic diagram it reset. H reset is coming from the GMCH to the processor. We can see in page number 7 also. Here there is a mistake. This arrow should not be inside, it should be outside. Now we go to the, so we have covered the entire powering on a processor for a ICH type of board, right? ICH type of board. We have followed the Intel data sheet, PLT reset. After PLT reset gets, let's go to the next page. Sorry, after the processor gets PLT resets, you see the PLT reset, stop clock is there. Stop clock is for not very much important, but this processor samples a stop clock, so you can see a stop clock is here. We can also search for this stop clock. We can also search for this stop clock, and you see, let's search it. Stop clock. Stop clock, you see, it's going to the page number 4. The ICH is generating this stop clock signal to the CPU. This H stop clock, you just copy it, and the sequence is that a stop clock will get generated after PLT reset, after, you see, a stop clock. So we follow the sequence, and in the sequence we see PLT reset is generated. After PLT reset is generated, the CPU reset will generate. Here it's not shown because CPU reset signal is not related with the ICH. So the Intel have not shown this CPU reset signal over here. So that's why I have put this image over here. The CPU reset will go to the CPU. CPU will start reading BIOS and and you see processor interface signal will generate strap values. You see what does this means? Will generate strap values. Strap values indicate to the processor to, like, from where to read the BIOS. Suppose in a notebook motherboard 2-3 BIOS chip is connected, one with the ICH, another with the EC. From where the CPU will read the BIOS, that thing is indicated by the strap values, and we will go and study this strap value when we will cover the next topic, and the next topic is soft start of processor. We had already covered the entire hard start for a ICH 8 type of board. I will discuss the same procedure for a Intel Series 5 chipset, for a Intel Series 6 chipset, and when you study all these three things, we'll correlate everything. So I will finish this class with this note, and in my next class I will cover the Intel Series 5 chipset and Intel Series 6 chipset, and then I will cover the soft start, like how the processor reads the BIOS, what are the various signals generated, how can we test that the CPU is reading the BIOS after powering on, and how display is generated. That will help us to solve the problem of no display conditions. And after I finish this two comparisons of Intel Series 5 and 6, I will test each of these things that I have spoken practically, and I will show you how to test each of these things practically, and we also solve problems step by step, like how to solve dead problem, how to solve no display problem. So thank you for this class, and my next class will be very soon, and I would prefer to finish this course as soon as possible. Thank you. companies. So what we have to check while we are going to see how this board will work, we have to just see the Intel chipsets. So I have taken example board, that is HP R12 schematic diagram. So I will be discussing the signals with reference to the HP R12 schematics. So let's go to the data sheet first. What is the Intel Series 5 chipset? And we'll just slowly browse this data sheet and we'll go through the important points, and I will revise the important points what we had discussed in the previous class also, if I find so. So let's go to let's quickly browse this data sheet, and we go to the next page, and all of these are just content for, and our most important thing is the electrical characteristic that I had already told in my previous class. What you have to refer in the data sheet is electrical characteristics. But I'm just going to slowly quickly to this data sheet in order to look anything important if we find in this data sheet. So this is a brief description of Intel Series 5 chipset. And what is the brief description? The brief description is it supports direct media interface, that we already see in the data sheet. You can see it supports DMI, direct media interface, and then it is having a PCI Express. Is correct. It is having a PCI bus interface, no longer used, but it supports. Then it is having a serial ATA host controller and Intel rapid storage technology and USB 2.0. And the most important is Intel active management technology, and we'll discuss about the management engine, how the management engine works, and what has been the origin of management engine, and we'll also solve the problem of the cleaning, how to clean the AMI region in a BIOS. That is very important and currently very hot topic in the repairing areas, right? And it has power management logic. So we'll just quickly go and see the important points. Same RTC clock, same as ICH9, right? So let's go and click to browse. So this data, so you can see this is applicable to P55, H55, H57. This is desktop and this is laptop. That is HM55, HM57, QM57, PM55. This is for notebook. So we go and let's quickly go through. If you find any other important things, just mention. So this is all the thing. Wait a minute. If you find anything important, let's discuss. Well, this is not all required for a recurring, but if you had a proper concept, you can analyze anything. You can analyze any kind of board, right? So this is RTC. We had already discussed what does this is the Intel active management technologies, and we'll discuss when we are discussing the AMI region, right? So just go carefully and alright. So this is a SKU, and nothing important here. Yeah, so I'll just you can see this line is very important. I have already discussed this point while I was discussing about the ICH9. A signal is considered to be, you can see, a signal is considered to be in the functional operating mode after RTC reset deasserts for signals in the RTC well, after RSM reset deasserts for signal in the suspend well, and after PWR power OK assert for signal in the core well, and after LAN reset deassert for signal in the LAN well. As I've already told, there are many kind of power whales when we are discussing about the Intel chipset, whether it is a ICH or PCH. I have already told there are many power whales for this chipset. And what are those power whales? One is the RTC well, suspend well, core well, and LAN well. So which signals are in the RTC well? You can see when signal is considered to be functionally operating, when RTC reset signal deassert. When RTC signal deassert, then all signals in the RTC well will be functionally operated. If RTC RST do not deassert means this value should be high. If this value is not high, then no signals will be functionally operative. Functionally operative means that signal is functional in RTC well when we are talking about RTC well. Similarly, when we are talking about signals in the suspend well, when all the signals are operating in suspend well, when RSM reset deassert means it would be high, right? And when signals would be operating in core well, when power OK assert. Now this concept, this I have already discussed in the previous class. This is very important and the crux of explaining the power sequence. Alright, so I will cover this when we are going to discuss the power sequence of Intel Series 5 chips. I'll come back to this point. Alright, so we go to the next page and we find out if anything is, yeah, this is a basic block diagram of PCH, and you can see there are various kind of differences between a ICH and a PCH block diagram. You can just easily go through the differences, what differences you find out. Alright, and we'll also find differences in the power sequence. So this is a basic block diagram, and direct media interface DMI is there, PC Express is there, and firmware and hub interface is there. These are all the things we had already covered. PCI interface, this is no longer used now, but still it's there. And serial ATA interface, and you can see serial ATA interface. Let's go to the next page. This is all we had already discussed this thing. LPC interface is there, interrupt interface is there, USB interface is there. Well, sometimes some people ask me, so that how does the display come on the LCD, right? This has been a lot of class we have finished, but often a confusion is that how a display comes on the laptop screen. So I was thinking to tell you about this when I will go there at that stage, but some people have asked me, so I'll just discuss a little bit of this in this class only, and right now only. So let's go to the LVDS interface, because that is where LVDS interface is where how your display is generated, right? Your display is generated. So we'll go to the LVDS interface. Let's go. LVDS interface. This is clock signal. Alright. And this is LVDS interface. This is only in mobile. So how does a display is generated? Right? How a display is generated. So we go to the I will just discuss how the display is generated. Okay, so we were discussing like how the display comes to your screen. See, this CPU and this PCH, they interact via DMI, that is direct media interface, and they interact the data, right? They interact with the data, and like if CPU has to display, like if all power sequence has been completed, that everything is powered on. If we study, suppose we see the, let's go to the electrical characteristics, and we'll see it. Electrical characteristic, and we go to the power management timing diagram. Alright, so here you see the last state is from PCH, PLT resets goes to the processor. That is, a reset has been given to the processor. Now processor will start, and processor will go to the first address. that is the first address that is in the BIOS, right? That is in the BIOS. So the processor will look for that address. So it will by default look for an address which is in the BIOS. So this CPU will transfer the data to the PCH via DMI, and here when it is transferring or communicating data, then there are many kind of signal, that is data bus master BG, initiator ready, target ready, TRDY, IRDY, data bus master BG. So you can see all these kind of signals over here. And so first the CPU will look for that address, so it will send the data to the Intel PCH, and Intel PCH will go to the BIOS, that is SPI BIOS that is connected with this chip, and will read that data, will extract the data, and will display the BIOS setup via LVDS. And what is LVDS? LVDS is low voltage differential signaling. That is 40 pin. You can see over here. You can see here, this is a data sheet of a screen. This is a data sheet of a 15.6 LED. 15.6 LED. So I'm just going to tell you how display comes. You can see over here, as you see, a 40 pin cable is connected to the LVDS connector present on the notebook motherboard, and it is connected to the screen, right? It is connected to the screen. So let's see what are those. You can see this is a very basic diagram of a screen. So this LVDS cable comes here, DC power is given to the PCB board, and LED power is given, and there is a LVDS receiver. All the data would be received here, and it is converted in that some data is fed to the source driver and some data is fed to the gate. And inside the screen, inside any LED, there are TFT. TFT is thin film transistor. So the gate will activate that transistor, and the source data will be passed, and as you see inside the screen, there are two polarizer which are at 90 degree. Inside the screen there are two polarizer which are at 90 degree. So if you pass a light, they will not allow a light to pass. But when gate is activated, inside the glass, this thin film transistor will be positioned in such a direction that the light can pass, and with turning of this TFT, you can see the image. Why I am trying to tell you about this is that if you have a no display condition, you can just go straight away to the LVDS connector, and we can just see here, page number 7 is here and we just zoom it, and this is R12 schematic diagram. As I've already told you, I will be using a R12 schematic diagram. And let's go to this is LVDS section, a very important section, because this LVDS signal section converts the data which has processed by the CPU into a format which can be passed using, see, your motherboard is manufactured by a different company, your screen is manufactured by a different company. Then how can we communicate this data from a motherboard to a screen? There must be something which is same in both screen and motherboard. So what is same? Same is your LVDS part. This LVDS part is present on your motherboard also, and the LVDS part is present on your screen also. So the data is converted into a LVDS format, and that is sent via the cable to the screen, and then the screen will decode that data and decode the data and present. So we can see this is LVDS section, and you can see all the signals are going to the page number 20, which is a LVDS connector. You just go to the page number 20. You go to the page number 20 and you can see all the data is going to this LVDS connector, and here a cable would be connected, and that cable would be connected to the screen. So if your display is not coming, you have to check the following things. You have to check this 3-volt supply, right? Then you have to check the backlight enable, BLON you have to check, and you have to check all sorts of this data. You can EDID clock, and EDID data is for the EDID chip that is present on the LCD screen. The EDID chip on the LCD screen determine how the data has to be determine, that is whether it is a 14.1 LCD, 15.6 LCD, how the data has to be displayed, whether it is a wide resolution or HD or full HD. It all depends on the EDID. So you can check all these kind of signals over here. So the first step, while we have a no display condition, is to look for these signals. I will again come back to this question. I will again come back to the problem of no display, how to solve this no display. Right now I'm just giving a basic idea because it has been often asked by me, right? Often asked by me. So I'll come back at this problem again. So let's go again to the schematic diagram, and where we were in this page, I think, the functional description, right? So let's go straight to the electrical characteristic, because what we are discussing is the power sequence. So we go to the electrical characteristics, and we have to just go for the power sequencing and reset diagram. Yes, power sequencing and the reset diagram. Let's go to the next page. Yes, and so we'll start from here. Okay, so we'll just finish up with the power on sequence of the Intel Series 5 chipset. So this is the power management timing diagram, and the first signal is VCC RTC. As we have already discussed this signal in the previous class, let's go to the schematic diagram R12 that we are referring here, and we just search VCC RTC. Right, we just copy this and we'll paste it over here. Okay, and so this is going to VCC RTC. Yes, so you see VCC RTC is connected with the plus RTC underscore cell. So we just copy this, where this is coming from. This is the first step, as we had already discussed in the previous class also, that this is the first step. The VCC section is the first step. Let's go from where this is coming. So this is coming from here. This is coming from a plus 3V ECU and a battery, that is the RTC cell. Now you can see plus 3V PCU. From where this plus 3V PCU is coming, just copy this, plus 3V PCU plus 3V PCU, and this is definitely coming from the 3V 5V regulator IC, but we'll reach over there eventually. So if you trace the notebook motherboard with the power sequence that is present in the data sheet, then you will eventually locate the faulty component. That I have been repeating this thing from the last class only, that if you follow this procedure, you will eventually locate the faulty parts. So we have to check from where this plus 3V PCU is coming. It is definitely coming from the 3V 5V regulator IC, right? This is definitely coming from the 3V 5V regulator IC, but we are just finding and we had already discussed. So you can see this is 3 volt 5 volt regulator IC, and plus 3V PCU is connected to the V regulated 3, that is the 3 volt LDO. This is 3 volt LDO. So if this is not coming, then we have to check the V in of this IC, if V in is present or not. If V in is present but plus 3V PCU is not coming, then this IC is faulty. If V in is not coming, then we have to check for the V in. The same procedure that we have done for the earlier boards, right? So we go again. The next step is RTC reset. What is the source? From board to PCS, that is RTC reset is an input. This is an input. So we go and find it, search it over here again. RTC reset, you can see this is connected to the RTC reset pin, and we'll see from where this is coming. RTC reset, so you can see this is all RTC reset, SRTC reset, SM underscore computer is all connected with the plus 3V PCU. So if plus 3V PCU is coming, then your RTC section is getting signal. If this plus 3V PCU is not getting, then these all are not getting. So your notebook motherboard has not yet started, right? Sometime your battery connector gets sorted, then also you will not find the signals. This I have already told. So we go again in the sequence and we find VCC sus. What is VCC sus? And you can see in the previous class also I have spoken what is VCC sus, right? We'll see about the VCC sus. What are the voltages which are included in the VCC sus? It's very important to revise all these things again and again, because this is the crux of your notebook diagnostic skills, right? VCC sus. We can go and straight away find it in our schematic diagram. VCC sus. So this VCC sus, no, this is not VCC sus, this is VCC sus 3_3. We have to find the VCC sus, right? Okay, so the next signal in the sequence is VCC sus. As I have already told in the previous class, there is no such voltage called VCC sus in the notebook motherboard. Rather, this VCC sus includes many type of voltages, like 3 kind of voltage. Together they are called VCC sus. So let's again see what are the voltages which compromises of VCC sus. And here you can see VCC sus supplies include VCC sus 3_3, V5 reference underscore sus, VCC sus HDA, VCC LAN, and VCC AMI 3_3 and VCC AMI. So when we are talking about VCC sus, we are talking about all of these voltages. So we'll see in the schematic from where all these voltages are coming and how to check them, right? So let's search in the schematic VCC sus 3_3. That is the first step, right? That is the first voltages in VCC sus. So you can see this VCC sus 3_3 is connected with plus 3VS5. Now we'll check from where this plus 3VS5 is coming, right? Plus 3VS5, and we'll go again to the 3 volt 5 volt regulator IC. Alright, so you can see this plus 3VS5 is generated by the 3 volt 5 volt regulator after switching this MOSFETs, right? After switching this MOSFETs. So this is 3 volt plus 3VS5 is generated from this regulator after switching. So there must be enable, right? There must be enable in order to enable this regulator. All right, so we'll check where is the enable pin. And you can see this is ENC. ENC is connected with the S5 underscore on, which will enable these regulators, this regulator and this regulator, both regulator, to generate the plus 3VS5 and plus 5VS5. Now you can see from where this S5 underscore on is generated, and this is coming from page number 29. That certainly means IO controller page, but we will again search this, and you can see this S5 underscore on is coming from the IO controller page. This is ECKB3926, right? So this is S5 underscore on is coming from the IO controller. So when we are checking the VCC sus, that simply means the VCC sus is generated, is consisting of many kind of voltages. It consisting of VCC sus 3 underscore 3, V5 reference, VCC sus SDA, VCC LAN. To provide the VCC sus 3 underscore 3, the IO controller is generating S5 underscore on signal, and this S5 underscore on signal is going to the 3 volt 5 volt regulator IC, and it will switch MOSFETs to generate this plus 3VS5. So this plus 3VS5 is not generated, then we have to look for these two MOSFETs, we have to look for this coil, and we have to look for this IC, and we have to look for this S5 underscore on. So if this S5 underscore on is not generated, then we have to look for the EC working condition, that is the supply, reset and clock, right? Supply, reset, clock and reading with the BIOS, the EC reading with the EC BIOS. So if your S5 underscore on is not coming, you have to check the EC working condition. If it's coming, then we have to check these two MOSFETs, you have to check this coil, you have to check this capacitors. So in this way, if we trace, then we will eventually go to the faulty locations. So if we have checked VCC sus, that means we have checked the IO controller and the 3 volt 5 volt regulator completely. That simply means we have checked the 3 volt 5 volt regulator IC and the IO controller completely. And we'll again look for the other signal. This is V5 REF sus. V5 REF sus. So we'll just paste it over here. And you can see this V5 REF sus is connected with the plus 5VS5, and this plus 5VS5 is coming from the 3 volt 5 volt regulator IC, right? You can see here plus 5VS5, the same condition. S5 underscore on will give the enable signal, this two MOSFET will switch and it will generate the plus 5V voltage. And you can also look for the similarly all these three voltages. Another thing is VCC AMI 3 underscore 3. We also have to look for these two voltages. If Intel AMI is powered in S3, S4, S5. In some cases, the Intel management engine is powered in S3, S4, S5, and in some cases it is powered in S0 condition. We can also look here. We can just copy and we can just paste it over here, and just we can look, and you can see this is connected with the plus 3V voltages. Plus 3V is generated in S0 condition, right? It is generated in S0 condition, so we don't have to look for this right now. Alright, so we just go to the next signal. And what is the next signal? RSM reset hash. We just copy this and we'll put it here. RSM reset hash. RSM reset hash. And that when we are searching for a signal RSM reset, always we talk about inside the chip, we never talk outside the chip. So we mean by this point RSM reset, and this is input to the PCH. This RSM reset signal is getting generated from page number 29. That means we have to go to the IO controller page, right? Page number 29, and we just go in page number 29, and you can see this is being generated from the IO controller page. And we have already discussed how this RSM reset generate. RSM reset generate when your IO controller gets, that is EC in your IO gets three things: supply, reset and clock. And when you press power button, then this RSM reset will generate. So if your RSM reset is not generated, then you have to look for many things. First you have to look for supply, reset, clock, and EC and BIOS interaction, and that is EC with this BIOS interaction. And you have to also check the adapter, whether your EC is sensing adapter or not. That is whether your EC is sensing adapter AC in, right? Whether your adapter is sensing the AC in or not. So that is the case. All this we have already discussed about the EC working condition. So after RSM reset, now what? After RSM reset is sus clock, and we have already discussed what is sus clock. Sus clock is suspend clock, and this is used for refresh. This is used for refresh, memory refresh, because at this point of time there is no clock generator turning on, so we have to just rely on the suspend clock. And you can see in the suspend clock, we just search this suspend clock. Sometime it is used, sometime it may not be used. You can see this sus clock. Yeah, so you can see this sus clock is connected to the PCH sus clock underscore L. So we just copy this from where this is coming. This is an output from the PCH. This is an output from the PCH. So PCH underscore SUSCLK underscore L, right? I think I did some mistake. This is secure. This PDF is secure, so you cannot copy and paste, right? So this is going via register, and this is getting converted into the PCH sus clock. Again, we can search it over here. PCH sus clock, where this is going? This PCH sus clock is going to the crystal CRY2. This is, so that means as we have already talked, the sus clock is basically the output. There is an internal when we were talking about the RTC section, I have already told this input, this clock, this XCLK1 clock is input is amplified and getting out from O, that is output, that is getting output from O. So if you measure by a CRO over here, then you will get a small wave, you will get a small square wave, whereas if you measure by a CRO over here, you will get a full sine wave, that is you will get a full sine wave. So that is the sus clock, that is this sus clock. This way we can test whether this sus clock has come or not, and whether your RTC section has worked or not. So we go to the next point, and the next is SLP underscore S5. This SLP underscore S5 is for the power management. We have already discussed. We'll again discuss about SLP S5, SLP S4 and SLP S3. Alright. Okay, so the next signal that we are looking for is SLP underscore S5. As in the previous class, I have told you that SLP underscore S5, SLP underscore S4, SLP underscore S3, and SLP underscore SM are basically for the power plane control, right? Power plane control. So let's see SLP underscore S5, 4, 3 and M in the schematic diagram where they are. So let's search over here SLP underscore S5. Alright, so this SLP underscore S5 is an output signal from the PCH and it's going to the page number 29. So we can go straight to the page number 29, and this is an IO controller page. So your SLP underscore S5 is going to the IO controller, right? This is going to the IO controller. So SLP underscore S5, you can see this is an input to the pin number 25 of the IO controller. Similarly in our data sheet, if we check SLP underscore 4 and 3, and this 4 and 3 are basically over here. You can check this 4 is sus B, you see, sus C, sus B. Sus B is 4, sus C. We can check this thing, SLP underscore S4, and you can see 4 is sus C, B is sus B, SLP underscore S3 is sus B, SLP underscore S4 is sus C. So this is going to the page number 29. You can see page number 29. So sus C, sus B and SLP underscore S5. If the IO controller get this signal SLP underscore S5, sus B, sus C, that is SLP underscore S5, SLP underscore S3, SLP underscore S4, then this IO controller will output sus on, main on and VR on. Sus on, main on and VR on, right? Sus on, main on and VR on. And we can check what are the function of sus on. Sus on, you can see this sus on and main on is going to the RAM regulator. So this will generate the 1.5 voltage for the RAM, right? 1.5 voltage for the RAM. 1.5 means this is a DDR3 RAM based board, and this is DDR VTT REA. When you give main on, then this will generate the termination voltages for the RAM. So sus on and main on are generated by the IO controller when SLP underscore S4, SLP underscore S3 is received by the IO controller. And also VR on is generated. VR we go back to the page number 29, and you can see in the page number 29 sus on, main on, sus B, sus B, sus C. So and what it is outputting, sus on, main on and also VR on, VR underscore on. You can see VR underscore on. Where is it VR underscore on going? It must be going to the core regulator, the CPU core regulator. Yes, you can see this is going to the CPU core regulator. So we are already discussed in the previous class how this CPU core regulator works. First we must check VCC, second we must check RAM, third we must check this enable, fourth this VID pins, then VID pins, then this will drive high, drive low, this MOSFET will switch and it will generate the core voltages. After this core voltage is generated, then this voltage regulator will output clock enable hash in order to enable the clock generator chip. So we go back to the data sheet and we can see SLP underscore S5, SLP underscore S4, SLP underscore S3. Let's check how SLP underscore M works, right? Okay, so let's check the SLP underscore M signal. We go into the data sheet and find for the SLP underscore M signal, SLP underscore M, and we can see this SLP underscore M signal is not connected. So in this board the ME region has not been used. So we go and look the next signal. And what is the next signal? The next is VCC-ME. That is, VCC-ME is the voltage for the ME region in the PCH. But as we have seen, the SLP_M is not used, so this VCC-ME must be grounded, and we can check in the data sheet VCC-ME, and you can see the VCC-ME is all grounded. This is all grounded. You can see this all VCC-ME has been grounded because the SLP_M signal has not been used. So we go to the data sheet again, the Intel Series 5 chipset data sheet, and what is our next signal? VCC. And as we have seen in the earlier board, this VCC compromises of many kind of voltages, and we have to check all of them one by one. And if we are able to check all of them one by one, then if there is any faulty location, we can locate it. We can just isolate that problem. So let's go and see what compromises VCC. It's clearly written VCC includes VCC IO, VCC core, VCC 3_3, VCC ADPLLA, VCC ADPLLB, and VCC ADAC, V5REF, V_CP_IO, and all these voltages. So let's check all these voltages one by one. We will start with VCC IO, and we just paste it over here, VCC IO, and you can see the VCC IO is connected to plus 1.05 volt. So we have to search for plus 1.05 volt, from where this plus 1.05 volt is coming, right? Just look, we have to locate that regulator. Now obviously it is coming from 1.05 volt regulator IC. We'll just see ourselves. No, not this one. 1.05 volt, 1.05 volt, and you can see this is 1.05, and in the schematic you can see plus 1.05 volt regulator. And how this plus 1.05 is generated? This is generated from this regulator IC, and you can see the enable pin is connected with the main on. This main on signal has already been generated by the IO controller after IO controller gets SLPS4 and SLPS3. So this IO controller generates main on. This is the enable pin. This regulator will switch these MOSFETs, to generate plus 1.05 volt, and this plus 1.05 volt is the VCC IO. So if we check like this, then if any faulty components, we can locate that faulty component. We will check for these regulators, we will check for these MOSFETs. If plus 1.05 volt is not coming, in that case we are going to isolate that problem. Let's see the another voltage. This is VCC core. We'll just copy this and we'll paste it over here. VCC core. This VCC core is again connected with plus 1.05 volt. So we had already checked how this plus 1.05 volt is generated. So now we check another VCC 3_3. VCC 3_3. We put in the data sheet VCC 3_3. This VCC 3_3 is connected with plus 3V volt. Obviously this plus 3V volt would be generated from 3V PCU, but how it is generated, we'll see in the data sheet. Plus 3V. Let's check how this plus 3V is generated. Plus 3V, right? Plus 3V. Wait. Plus 3V. Now this is plus 3V_LDO. So we go again to search how this plus 3V is generated. Not yet. Plus 3V, no. Plus 3V, no. Not in this space. Somewhere very small circuit, and this is very important because sometimes your plus 3V volt is not coming. Then in that case also your board won't turn on. Right? Plus 3V. we have to find how this plus 3v is generated, right? Plus 3v, no, not here, no, plus 3v, not here, not here, not here, not here, plus 3v, no, we have to find from where this plus 3v is coming. Yes, not here. There is a very small page where it would be written that EE conversion plus 3v, and we are just going to find out somewhere this must get converted. This 3 volt from the regulator IC must get converted to plus 3v. That is very important, and we have to just see from where this is coming, right? From where this is coming. Plus 3v, not this is plus 3v PCB, no, not this space. Just check somewhere very small. Plus 3v, yes, you can see this is very important. Change from plus 3vs5 to plus 3v for EE information, right? So how this plus 3vs5 is getting converted into plus 3v, you can check over here. DZPU underscore PR underscore EN is a signal coming from the PCH, right? This is going into this gate of this MOSFET. Since this is an n-channel MOSFET, the gate receive voltage, this gets activated. This gets activated means that means the V-in will drop here. The V-in will drop. This circuit will get activated. This V-in will drop here. Since this V-in will drop here, the gate would get activated, and this will get activated, and this gate is also connected over here. This gate would also get activated. This gate gets activated, that means this MOSFET gets activated. So plus 3vs5 is getting connected to the plus 3v. This is very important. This is for the discrete. Similarly, you will find it for UMA. Right? So this is how plus 3v is getting converted. Now we next see, we can check for the other signals also. I'll just look for this one, V5 REF, and we just test it over here, V5 REF, and V5 REF. You can see this V5 REF is connected to plus 5 volt, plus 5V. Now we have to check from there where this plus 5V is coming, right? Plus 5V is coming. Let's check. This is a very minute, right? This is a very minute thing, and we have to just locate from where this plus 5V, how this plus 5V is getting converted, right? How this plus 5V is getting converted. We have to just check this thing. Let's go and find again plus 5V. Not here, not here, no, not at all. Plus 5V. Let's check for where this plus 5 is coming. No. Plus 5V. But this is for the USB. Change to plus 5V. Plus 5 PCA now. Plus 5V. Not here. Obviously this plus 5V must be coming from this plus 5VS5, what we have to locate from where this is coming, right? From where this is coming, plus 5V. Not here, not here, not here. Plus 5V. Somewhere very minute thing. Yes, I think this plus 5V, you can see this is coming from main D. This is getting to the gate, and this plus 5VS5 is getting converted to the plus 5 volts. So these are very small portions of circuit where we have to check how these are converted. These are getting converted into, and here also you can see main drive 3.3, this plus 3VS5 is getting converted into plus 3V volt, because if this gate is connected, this is an N channel MOSFET, this gate is connected, this MOSFET will turn on, so drain to source gets connected, plus 5V SV is converted into plus 5 volt, and 3.3 volt is converted into plus 3V volt. So this is how 5 volt and 3 volt is getting converted from plus 5VS5 and plus 3VS5. And as you see, when we are checking this, we are also checking this IC, that is the discharge IC G5934. We have to check, this is the discharge IC, right? This is the discharge IC. So while we are checking for this, we have to check for this main D, right? We have to check for this main D. So this is how plus 3V volt and plus 5V volt are getting generated from plus 3VS5 and plus 5VS5 respectively, right? So if you follow the data sheet, if you follow checking all these things, then eventually we are going to check everything in the circuit. But this is the step by which we have to check in the circuit diagram. Let's go back, and suppose we have checked VCC. Suppose we have checked VCC. Now what we have to check? VCC underscore CPU. VCC underscore CPU. So we just VCC underscore CPU. We just go in the schematic diagram. This is basically the voltage, the core voltages from the board to the processor, that after PCH receives VCC, what is VCC CPU? So what we can do is we just go to the core regulator sorry, we just go to the core regulator, and here in the core regulator you can see the core voltage, the plus V core is getting generated, the plus V core is getting generated, right? So if all the VCC voltage is getting generated, if all the VCC is getting generated, after this the CPU core voltage gets generated, and the CPU core, after the CPU core voltage is getting generated, the processor VRM will give an input of system power OK. You can see system power OK, SYS underscore PWR OK, SYS underscore PWR OK. And you can see the sys power OK is coming from IMVP power good, and you can see this IMVP power good is coming from the core voltage regulator. You can see this IMVP power good is the power good of core voltage regulator. So this is the relationship, that is, this is the relationship. After the board generates the core voltage, the processor will generate a system power OK, which is connected to the IMVP power good, an IMVP power good is output of core voltage regulator after it generates the core voltage correctly. Another input to the PCH is power OK, and we can see the power OK, PWR OK, PWR OK. Let's check PWR OK. You see this PWR OK is again connected with the IMVP power good, which is an output of the core voltage regulator IC. And after this, what is AMI power OK? Now this AMI power OK, you can see here it is connected with the EC power OK, and you can see this EC power OK will be coming from page number 29 from the IO controller page. Basically EC power OK, you can see the EC power OK comes out from the IO controller, right? This EC power OK is coming out from the IO controller page. That is, you see the sus on, main on, VR on is being generated from this IO controller page. From this IO controller, the VR on is going to the core voltage regulator page. The core voltage CPU is generating the CPU core voltages. After the CPU core voltage is being generated, this IO controller will generate EC power OK, right? That is EC power OK, that the embedded controller power OK signal, right? Embedded controller power OK signal would be generated, because you can see when EC power OK is generated, when the IO controller receives the hardware power good, and you can see it is this hardware power good, it is being coming out from many pages 331, 32, 35, 38, 39. Let's consider we go to the page number 38. You can see and this all regulators power good, HWPG, you can see this HWPG, all the regulators are generating this HWPG, and it is going to the IO controller, right? It is going to the IO controller. After the IO controller receives the hardware power good from all the regulator, it will generate EC power OK, right? It will generate EC power OK, EC PWR OK signal, and this is an input to the IO controller, because the IO controller is at the center of power management signal. We have already seen when EC receive SLP underscore S5, when EC receives sus B, when EC receives sus C, then it generate main on, sus on, and VR, main on, sus on, and VR on. This sus on, main on, and VR on open up all the voltage on the regulator, all the voltage on the main board. So all the voltage regulator will give a hardware power good signal to the IO controller. After IO controller receive the hardware power good, it will generate EC power OK signal, and this EC power OK signal is being fed to the AMI power OK, that is management engine power OK. So this is the relationship of how IO controller works in connection with the PCH, right? Okay, so we have seen signal up to AMI power OK. Now let's check the next signal, which is LAN underscore RST. So what we'll do is we'll just copy this and we'll just put it over here, LAN reset, LAN reset. And you can see this LAN reset, you can see it is getting connected over here. I think the LAN value is not used in this schematic, and that's why it is going to be grounded. You see this LAN reset, this is the LAN reset pin inside the PCH, and here this signal is RSV underscore ICH underscore LAN underscore RST, and you can see this is getting connected because the Intel LAN is not used over here. Why this is grounded is because we are not using the Intel PHY devices. This is called PHY devices. The Intel internal LAN is not used, and so you can see this is grounded. Now we go in the data sheet and check the next signal. This is DRAM power good. Sometime in your schematic diagram you will find this as DRAM power okay, because this is a signal which is coming out from the PCH and going to the processor to indicate to processor that yes, that DRAM power is okay, because in PCH kind of board the memory controller is inside the processor, right? The memory controller is inside the processor, so there must be some kind of indication to processor that the RAM power supply is not okay, right? That the RAM power supply is not okay because the memory controller is inside the processor. Otherwise, in a board which is having north bridge and south bridge, this indication would be sent to north bridge because the memory controller is inside the north bridge. But here the memory controller is inside the processor, so a signal must